In this section, we're going to look at how to solve exponential and logarithmic equations. So in this video, we're going to look at just exponential equations, and then in the next video, we'll tackle logarithmic equations. So think about what we've already learned about exponential functions. We know that we recognize exponential functions by the fact that the variable appears in the exponent position. And we also learned from graphing exponentials that the domain of an exponential function is all real numbers. So what that means to us in terms of equations is that I do not have to check my solutions unless I'm just wanting to check my work. I'm not going to run into any extraneous solutions or any solutions that will need to be thrown out because of that domain of all real numbers. Now, like any equation, I want to isolate the variable. So I want to get x alone on one side to solve the equation. Now, with exponential equations, that means getting the variable out of the exponent position. Now, my first two examples are going to show you a little bit of a shortcut that can be used if you recognize the shortcut and if the shortcut is possible or not. Now, for the shortcut to be possible, what I'm looking for is to see if both sides of the equation can be written with the same base. So in number one, you can see that the bases are already the same. So the base in both of these exponential expressions are 5. So what the shortcut says is that if I have 5 raised to some number or some value x, and it's equivalent to 5 being raised to another value, that those exponents must be equivalent to each other. So the only way that 5 to the x can equal 5 to the 8th power is if those exponents are equivalent to each other. So that's only true if x is equal to 8. So if I can get my bases to be the same on both sides of the equation, then I can use this shortcut of just setting the exponents equal to each other. Now keep in mind there can't be any other terms on either side of the equation. So for example, if I had 5 to the x equals 5 to the 8th plus x, then I couldn't use this rule and set x equal to 8. So it's got to be a single term on either side with the bases the same. So if you look at number 2, if I'm looking to see if I can use this shortcut, what I'm looking to identify is whether both of these can be raised to the same power, or I'm sorry, can be written as the same base. So really what I'm asking myself in my head is, can I write 16 as a base with 4? And I can, because I know that 4 to the second power is equal to 16. So if I do that first and rewrite this as 4 to the 3x power equals 4 to the second power, now I have both bases the same on both sides of the equal sign, which allows me to set my exponents equivalent to each other. And then this would take just one more little algebra step to get my solution. I would have to divide both sides by 3, and there would be the solution to the equation, x is equal to 2/3. So if you recognize this as being possible, you can definitely use the shortcut. Now the problem is, of course, most things can't be written as an exponential function or equation or term with the same base. You normally can't get those bases to be the same. So if you recognize that you can't get bases the same, or maybe you weren't looking for it and forgot to look for it, here are the general steps that I'm going to follow for exponential equations. And that is that I first want to isolate the term that contains that exponential variable. So you might have to add, subtract, or divide in order for that to happen. And then this is why we learned how to go back and forth, because what I'm going to do is I'm now going to rewrite it as a logarithm that I will then be able to evaluate with the assistance of a calculator. So let's take a look at number 3. So the first step is to isolate the base with its power, which is already done. There's nothing on that left-hand side with the 3 to the x that needs to be moved. So I'm ready to go straight to this second step, which is to rewrite it as a logarithm. So remember, the way that we do that is we say that the exponent is equal to the log, where my base of my log is the same as the base in the exponential expression, so my base is 3, and my argument is what the exponential expression is set equal to, which in this case is 36. So I want to know what the log base 3 of 36 is for this solution to this equation. So remember, to evaluate a logarithm that's not a base 10 or a base e, I need the change of base formula. So the change of base formula says that I can evaluate this by taking the natural log of the argument and dividing by the natural log of the base. So now I need my calculator. So that's why you see the calculator there on my screen. So I'm going to take the natural log of 36, close that parenthesis, and divide by the natural log of 3. And I'll round my answer to the nearest hundredth. So x is equal to 3.26. Now, because I'm rounding my answer, if you plug that back in and checked your solution, you wouldn't get exactly 36, but you would get close enough to know whether your answer seemed correct. Okay, number 4. So on number 4, we first have to isolate that term that contains the exponent. So this 6 to the 2x minus 3 needs to be alone on that side first before I can rewrite it as a logarithm. So that just means subtracting the 8 from both sides. So I've got 6 to the 2x minus 3 is equal to 7. Now I'm ready to rewrite it as a logarithm. So to do that, it's my exponent, which in this case is 2x minus 3. Let me rewrite that. So 2x minus 3 equals my log. My base is the same as the base in the exponential expression, so my base is 6, and my argument is 7. And now what you can do is you can isolate the x, add the 3 and divide by the 2, or you can go ahead and figure out what log base 6 of 7 is first. So remember, to figure out that, I'm going to use my change of base. So it's the natural log of the argument over the natural log of the base. So get on your calculator to figure out that. So natural log of 7 divided by the natural log of 6 is equal to 1.086. Now, I'm not finished with all my algebra, so you might want to give yourself a few decimal places in this evaluation of that log and not round your answer too soon. So you might want to wait and round your answer after you get x alone. So now I can do the rest on my calculator. I'm going to add 3 to both sides, which of course is just going to make that 4.086033. And then I want to divide that by 2. So if I add my 3 and then divide by 2, I get my value of x is equal to 2. If we round to the nearest hundredths place, 2.04. And there's my solution to that equation. Okay, let's take a look at another one. Number 5, we've got an e in there, so we just have to remember when we change to a logarithm what that means for our log. But again, I first need to isolate the term that contains the exponent with the variable, so I need to isolate that e first before I rewrite it as a logarithm. So I need to get rid of the 2, so I'll subtract 2 from both sides, leaving me negative 5e to the 2x equals negative 2. And then I also have to divide out that coefficient of negative 2. So if I divide that -2 by a -5, it will make it positive 2/5. And now I can rewrite it as a logarithm. So if you've got a coefficient on your e, that coefficient has to get moved to the other side as well before you write it as a logarithm. So now we're going to write that as a natural log. So remember, it's my exponent equals my log. And since my base is e, the notation is to use ln. And my argument is 2/5. So I need to figure out what the natural log of 2/5 is. So the natural log of 2 divided by 5, make sure you close your parenthesis, and I get my natural log. So 2x is equal to -0.91629. And if I divide that by 2, I'll get my value for x. So x is going to equal -0.4, excuse me, -0.4, actually it should be 0.46. Let me erase that. It's getting ugly. My sneeze threw me off. So x is equal to -0.46 if I round to the nearest hundredth. Now, just make sure that you read the instructions when you're working the homework as to what you're supposed to round your answer to, so that you don't get things marked wrong just because you rounded to the wrong place value. Okay, so I've got 2 more examples on here. So if you want to try on your own, oh, these ones are tougher ones. Wait a minute, let me show you this one. Okay, notice on this one, what makes this a little bit tougher, why I said that, was because I've got 2 exponents that contain the variable. So normally that first step, we always isolate the term that contains the variable exponent, before we change to logs. In this case, when I've got 2 exponents that contain the variable, that's not possible. So what I'm going to do is go straight to the logarithm. Now, you've got a choice here, because we usually start off with exponent equals. And in this case, we have 2 exponents. Now, it does not matter which exponent you work with, but I would recommend that you start with the exponent that has the more complicated exponent. So in other words, when I look at this problem here, I've got an exponent of x and an exponent of x plus 2. So what I'm going to do is start with the exponent x plus 2 and write it as a logarithm from that perspective. So I'm going to have my exponent x plus 2 equal to my log, and my base, because I chose this x plus 2 as my exponent to start with, my base is 3. And then my argument is this whole thing on the other side. So my argument is 4 to the x. Now, if you didn't start with the x plus 2, and let's say you started with the x instead, you would have exponent equals log, and my base would be 4, and my argument would be 3 to the x plus 2. And that's okay too. You can still solve the problem regardless of which exponent you start with. The algebra is just a little bit easier if you start with the exponent that's just got a little bit more complication to it. It's got an extra term in the exponent. Okay, so continuing on with this one here where I started, x plus 2 equals my log. What I now want to do is I want to figure out what this log is, but I want to get rid of this exponent that's in my argument. And remember, we had a property that told us how we can do that. We can do that by pulling the exponent on the argument out in front of the logarithm. So if I do that, I'm going to have x plus 2 equals x times log base 3 of 4. And now I can go ahead and evaluate what this logarithm is equal to. But you don't want to do that until you've gotten rid of that exponent from that position, until you've moved that exponent out in front. So on my calculator, I want to use my change of base formula. So remember, that means that I'm doing the natural log of the argument divided by the natural log of the base. So natural log of 4 divided by natural log of 3. And I can go ahead and fill that in. So I've got x plus 2 equals x times. And again, I don't want to round my answer too close on this one because I've got quite a bit of algebra yet to do. So I'll just keep all of it. Probably don't have to keep all of it, but at least keep 5 or 6 decimal places. Okay, now what I want to do is treat this like any other linear equation that I would solve. I want to get the x's on one side, the constants on the other, and then isolate x. So I'm going to go ahead and subtract this x from both sides. So that's going to leave me my 2 alone on the left. And then I want to just subtract, this is my coefficient here. And we usually write it in front of the x, but I want to subtract 1x from that. So if I subtract 1 from that coefficient, my coefficient will become 0.26, 1859507, and my variable x. And now all I want to do to get my x alone is to divide both sides by that decimal. And I won't write it all down there, but I'm going to divide by the full decimal. So I'm going to show you on the calculator. When I subtracted 1 from there, I got that 0.26 decimal. Now I want to take 2 and divide by that. So I'm going to do 2 divided by, and then you have this key down here that has ANS. So what that means, if you select that, is it's going to fill in with the last answer on your screen, which is what I want to divide 2 by. So to get that, I'm going to go to the second key and then hit that negative symbol, and it comes up with ANS for last answer. And if I hit enter, there's my solution. And now I can go ahead and round to the nearest hundredth, and I get x is equal to 7.64. Okay, now if you want to pause and try one of these tougher ones on your own and mimic those steps and see if you get the right answer, and then come back and check yourself. So I'm going to start this problem by rewriting it as a logarithm, where I'm going to start with the more complicated exponent. So x minus 1 has more terms than the other exponent, which is just x. So I'm going to start with that exponent. So my exponent equals my log, and the base on that power is 2, and what it's equal to is my argument. So my argument is 5 to the x power. Now the first thing I'm going to do is move that exponent out in front of my logarithm. So I'm going to have x minus 1 equals x times log base 2 of 5. I want it to get to the point where I don't have any variables in the argument of that log. Is now I can get on my calculator, use the change of base, natural log of the argument over natural log of the base, and I can fill in the decimal approximation of that. So the natural log of 5 divided by the natural log of 2 gives me that decimal. So I've got x minus 1 equals, and this time I'm going to go ahead and put that number first because it is the coefficient of my x value. So 321928095 x. And now I'm going to get my x's together on one side and then get my x alone. So I'll leave my -1 where it's at, and I'll subtract that x from both sides. So that'll leave me -1 on the left, and then I want to take this big old decimal coefficient and subtract that 1 coefficient. So again, I'll show it to you on the calculator. I'm going to subtract 1 and get 1.32192809.5x. And now to get x alone, I'm going to divide both sides by that big long decimal. I'm not writing it all out, but I am going to divide, by that whole decimal. So on my calculator, I'm going to type in my -1, and I want to divide by that last decimal that's on my screen. So I'm going to hit my division sign, and then my second answer key, and hit enter. And now I can round my answer to the nearest hundredth. So x is equal to -0.76. So those are the tougher of the types of exponential equations that you might run into. Probably the majority of the ones that you'll see in homework, at least to start, are going to be like those first three, where you have to isolate that exponential expression first and then change to a logarithm. But if there's anything in the video that bothers you, or if you run into any questions in your homework, make sure you email me.